Hey everybody, today we're looking at solution concentrations. In previous video lessons we kind of looked at how solutions form and what solutions are, but in this one we're going to look at more of the mathematical ways of describing solutions. So we talked about saturated, we talked about unsaturated, we talked about concentrated, dilute. What we're going to do now here is we're going to actually quantify that. So we talked qualitatively about solutions, now we're going to talk quantitatively. So we're going to start putting numbers to these because we want to know how much is in the solution, how many particles or how much is in there, because obviously when we deal with solutions, the problem is that we could put a lot of solute in or we could put a little bit of solute in. So the concentrations vary from solution to solution. So we have to have a very concrete way of describing solutions and how much is in there. And there's two ways that we're going to do this. One is known as mass percents. Now mass percents are kind of what you use in everyday life. If you buy a bottle of juice, it will tell you what concentration of the solution you're drinking is really made up of the actual juice itself. So mass percents, sometimes they're referred to as volume percents if you're doing things by volume, and other types of percentages, but we're going to stick with mass percent. And the mass percent is going to be based on the mass of the solute per 100 grams of solution. Okay, so we're going to deal with the solution. So we're going to deal with the percentage of how much mass. So for example, if we have a 5% sodium chloride solution, aqueous refers to sodium chloride being dissolved in the water. We have 5 grams of sodium chloride in every 100 grams of solution is essentially what that is telling us. Now be careful, because don't forget that your solution is made up of solute and solvent. So a lot of students forget this part when they deal with this, and they think of this as the solvent part. In this case, for the sodium chloride dissolved in water, they think of the 100 grams of it being the water part. It's not. It's the 100 grams of solution. So keep that in mind, that when we deal with the mass of solution, we have to add the solute plus the solvent here. Okay, so for my example of the sodium chloride, what mass of water is needed for every 100 grams of solution? We would need 95 grams of H2O, and we would need 5 grams of sodium chloride. So keep that in mind when you're dealing with mass percentages. So to find your mass percent, you're just going to use this equation down here. Oh, I forgot I had that written right here. Mass of the solute plus the mass of the solvent. So we take the mass of that solute over our total mass of solution and then multiply it by 100 to turn it to a percentage. And that's pretty much it. It's pretty straightforward. In this video I'm going to stick with just explaining the two ways that we deal with solutions, and then in another video I'll show you how to do the calculations, examples of the calculations. Okay? Alright, so when we deal with chemistry, okay, which we're going to move from what we do in everyday life to what we do in chemistry, the big thing is the mole. That's really what chemists are concerned with, is that molar quantity. So we want to talk about moles. So remember, we're dealing with molar, we're dealing with Avogadro's number of particles. So what molarity does, okay, this is molarity, it's a capital M, and this is going to tell us how many moles of solute are in 1 liter of solution. So if I have 1 liter of solution, it's going to tell me how many moles are in there. Remember, if you know the moles, you can then figure out the mass. So we can then go back and find out our mass percentage if we need. So there's a connection between mass percentages and molarities. So molarity is always going to refer to concentration. Now, a little note here. When you see these brackets like this, what that means is molarity. Okay, it really means concentration, but a lot of times when we see this, we're going to put units of molarity here, so we're going to use the capital M. Alright, so if I have brackets around sodium chloride, what I want you to tell me is what is the molarity of that solution. So the brackets refer to concentration. Okay, so every time you see those brackets, it means concentration. Alright, now one thing I would tell you, you're going to see this capital M over and over and over again in this chapter. Everywhere you see that M, I would cross it off and I would write moles per liter, because you want to recognize that what we're dealing with here is a unit that's moles per liter. We don't like writing this out all the time, so scientists or chemists use just the capital M. But I would suggest you write moles per liter, because it's going to remind you that this is a conversion factor. I'll talk about that in just a second. But this is a conversion factor, just like molar mass. Just like molar mass, and just like that kilojoules per mole stuff. So every time you see units over units like this, these are your conversion factors. So what does molarity mean? Well, let's take a look at an example. If I have a sugar solution and I tell you that it's 2.0 molar, what that means is that for every 1 liter of solution, it's going to contain 2 moles of sugar. That's what that tells me, because I'm going to take that 2.0 and I cross off the capital M and I put moles per liter, which means 2.0 moles for every 1 liter of solution. That's what that's telling me. Okay, so if I had 2 liters, I would double it and I would have 4 moles. If I had half a liter, I would have 1 mole. Okay, so that's what this number is telling us. So keep that in mind. Molarity, capital M, moles of solute per liters of solution, not milliliters, so watch that. So all you need to do in order to find your molarity is figure out how many moles you have and divide it by the volume of solution in liters. Okay, pretty straightforward. All right, oh, it's kind of weird. It looks kind of grayed out. Hopefully you can kind of see that. What molarity is or essentially, as I was saying earlier, is a conversion factor. So if I take that equation, moles per liter like this. Oh, look at that, magically fixed. Okay, moles per liter, that's what the unit that capital M is moles per liter. Well, if I solve for my moles, it would be moles are equal to the molarity times the liters, right? Which is what I'm doing down here. So you could say it's moles over volume. Essentially, we would say N over V, but you get the idea. So what I would do is if I take my moles, or I'm trying to solve for my moles, and I have molarity, all I need to know is what the volume is. Because for every volume I have, I can figure out the number of moles. So I would take that unit, rewrite it, and my volume is in liters. Those units cancel, and I can solve for moles. Okay, so what that means is that if you know the volume and the molarity, you can figure out the number of moles. Remember, in chemistry, if you haven't figured this out yet, guys, it's all about finding moles in a lot of these problems. So if I give you the mass of water, you could tell me how many moles of water you have. If I gave you the pressure, the volume, and the temperature of oxygen gas, you could tell me how many moles of oxygen gas. Okay, now in this chapter, if I give you the volume and the molarity, you are going to multiply those two together and get the number of moles. So watch for this phrase, a volume of a concentrated solution. Just remember that this has to be converted to liters, okay? So that's going to be very useful when we get to stoichiometry of solutions, all right? Now, 2 other things we need to look at. One is when we deal with ions. Because we deal with ionic compounds, we have to remember this idea of dissociation, okay? So when we put solutions, ionic compounds into solution, they're going to dissociate. Remember, dissociation just means to break up. I'm going to show you a little video here real quick, just kind of refresh your memory on this, and then I'll come back to this slide, okay? Okay, so as we were talking about before with the idea of dissolving, when we dissolve something like an ionic compound, like sodium chloride, into water, to us it looks just like this, white particles going into solution, and then we drink the solution, it tastes salty. What's actually happening at the microscopic level is pretty important here. So let me reset all this. If I were to put into solution something like sugar, okay, like the glucose, and I sprinkle this in here, okay, we could see that it breaks up into, so those little white crystals that were going in there are made up of billions and billions of these little molecules of glucose. Now they stay together as a group of glucose or sugar, right, because glucose is a type of sugar, okay, so they stay together. There's no dissociation here. This is just purely dissolving. The particles go into solution and you can't see them anymore. Now if I change this, and I go to sodium chloride, something different happens when I shake sodium chloride. Oops, let's put play. If I put sodium chloride into solution, what happens is these particles break up into multiple ions. So this is dissociation. So the difference here is that I have chloride ions, which are negative, which are the green ones, and I have sodium ions, which are positive. So that sodium chloride actually breaks up into ions. All ionic compounds do this when we dissolve them into water. It's referred to as dissociation. So we have to keep in mind when we are dealing with ionic compounds that we have not only the dissolving process, but we get that process of dissociation. All right. So let's go back to the notes. Okay. So as I was saying, as the sodium, in this case calcium chloride, gets put into water, it's going to dissociate into ions. And this is really important because when we think of ionic compounds, we don't think of them in groups like this, especially when they're dissolved. As a chemist, I see sodium or calcium chloride as ions. And this is really important here because I get twice as many chloride ions as I do calcium ions. And this throws students for a little bit of a loop in the beginning because it seems like it defies some of the laws that we talked about. So if I have 1 molar calcium chloride solution, it is going to contain 1 mole of calcium chloride. Okay, so for every 1 liter, I have 1 mole of calcium chloride ionic compound. But remember, it dissociates into calcium ions. So you could use stoichiometry here. If this is 1 mole, you would have 1 mole of calcium ion. So therefore, the concentration of those ions stays the same. But the chloride doubles. I get twice as many chloride ions in solution than I did originally. So actually, my concentration of the chloride ions goes up. Okay, if you go back and you look at that video, actually, you know what, let me just show you real quick. Okay, if I look here, my ions are even. I have the same number of sodium and the same number of chloride ions. But if I go to something like, I've got something somewhere, I think, calcium chloride, my example I was looking at right there. If I shake the calcium chloride into solution, watch what happens here. Breaks up into dissolving, right, dissolves, and then dissociates into the various ions. But look at the concentration of the chloride. Chloride is double that of the calcium, and that everybody's like, well, how can that be? How can I get more than I had originally starting off? Because I'm breaking it up into pieces. Think about this. If calcium chloride were a bicycle and you were to break the bicycle into pieces, you would have 1 seat and 2 tires. So if I had 1 dozen bicycles, how could I get 24 tires? Isn't that more than I started with? Same idea. I'm getting 2 chloride ions for every one of the compounds. And I think that's pretty good. I think we can continue on here. Okay. So I'll show you some calculations in the next lesson. I just want to talk about one last thing, which is something called the standard solution. Standard solutions, if we talk about these, and we use these quite a bit, is going to be a solution that has a known concentration, meaning that we know what the molarity is exactly. To create one of these, we need to know what concentration we need. Typically, we figure out what mass of solid, and I'll show you again this in the actual calculation section. I put that solid into what's known as a volumetric flask, and I pour a little bit of water in there, and I shake it up, and then I dilute it down to this mark here. And this mark would be the volume that I'm looking to achieve. That's what this mark is. And that's how you create a standard solution. So this solution would be precisely measured out so we would know exactly what that concentration is. Okay, so that should be enough background information. If you want to watch the next couple of videos, I don't want to, maybe 1, maybe 2, depending on what I do here. But I'll show you the example calculations for mass percent and for molarity. All right, thanks a lot.